Great. So I don't think Dr. Mahibian need much introduction anymore. So I'll just go quickly to where we are currently in the workshop, and then he can jump right in. One sec. All right. Perfect. So we're on to week 6 of McMedHacks. It's the first workshop of week 6, and we'll have another one this coming Wednesday. Today we'll implement our first UNet. So far you've seen supervised learning techniques, and yesterday we've had a wonderful seminar session from Dr. Anne Martel from University of Toronto Medical Biophysics unit that where she talked about weekly and self-supervised learning techniques for limited annotated data. And today we're going back to implementation of a UNet for real, seeing that live in code. Live land acknowledgement. If you don't know which land you're on, please go ahead and go follow that link. Our virtual event is based in Montreal, Quebec, which is the traditional territory of the Kanakahaka, and is on land which has long served as a meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse Indigenous peoples whose presence marks this territory on which peoples of the world not gather. We encourage you to learn and discuss about the history of the land on which you reside. So please remain muted during the presentation. So like I mentioned before, we're at week 6, and then week 7 will be our last week. For week 6, today is the first workshop, and as I mentioned before, we're implementing our first UNet in Google Colab and PyTorch. And on Wednesday, we'll have Dr. Katie Owens, one of Dr. Farhad Maliki's longtime collaborators, to talk about deep learning model generalizability, pitfalls, and best practices. There's a paper related to that. Personally enjoyed it very much, so they'll talk about it more. And we have 2 mentors this week. You have seen them before. First is Benjamin Weiser, and second is Moin Hassani. And are you guys in the audience?
There's a mistake. I think Cesare was the mentor. Ben and Cesare.
Okay.
But
yeah. Are you guys here? Did you guys want?
Here, yeah.
All right, cool. Do you guys want to say hi again?
I can quickly say hi. Hi. Yeah, I'm a master's student in NLP, researching the applications of NLP to family medicine. And yeah, I'm happy to be here. Happy to answer any questions about deep learning in general.
Sorry about that mistake. And what's Hussein, is the other mentor correct? Ben or no?
Ben, no, I helped with this. I don't think.
Okay. All right. Thank you so much, Cesar.
Yeah.
I'm sure everyone has remembered you from the previous workshop, and yeah, I don't think Dr. Mahibian need much introduction. This is the first workshop that he's giving for McMedHacks 2022. And I guess just briefly, he received his BSc and MSc degrees in biomedical engineering and PhD in electrical and computer engineering from University of Saskatchewan. And he's worked many years as machine learning engineer in industry in the fields of NLP and computer vision. So today he'll walk us through implementing our first UNet. Thank you very much. Alrighty.
Hi, everyone. Thank you for joining the workshop about implementing the UNet. Let me share my screen and start. So can you see my screen?
Yes, it's up.
Great. So what I've prepared here is I want to go first through the paper of UNet and read the paper a little bit. Then we will have implementation about image segmentation on brain images. And most of the credit of this code returned back to some of the kernels in the Kaggle. And I just got some different parts of the code from different kernels that was interesting and useful for this session. So let's jump to the paper and see what is UNet and why it is devised for image segmentation. So before going to the image segmentation by UNet, I think it is important to know that what other things we have in image domain computer vision. So I can categorize the computer vision in 3 or 4 different categories. The first one is the image object detection. And that was returned back to the old time that people trying to detect object on images just by using bounding boxes. So if you remember in some years back, some algorithms started working on object detection only, like YOLO, first versions of the YOLO algorithm. And in object detection, we only detect objects. And by object, we just create a box around it. We don't have any specific localization of that object. Then we have instance segmentation. That instance segmentation, there are 2 heads usually in the algorithm. We have boxes, but also from the boxes, we have another head that we try to get the exact location of instances. And also now with UNet, starting from UNet, we will have semantic segmentation, that each pixel can have a specific class to it. So the difference between instance segmentation and semantic segmentation should be understood based on, let me open my annotation. And or maybe it's better to see the difference between instance with semantic. If you just search in the Google, maybe there are some good pictures we can show. Yeah, here. So for example, if you see the semantic segmentation, if we create an algorithm for detecting person on an image, in semantic segmentation, we assign each pixel to one of the classes, and the model cannot determine that this person is different than another person. Each pixel should be, like, for example, in this case, 0 as background or 1 as person. And in instance segmentation, we will have exactly one object as person, so we can categorize person, we can count them. So if you want to compare the object detection, the semantic segmentation, and instance segmentation, the object detection, as I said, we only have boxes. In semantic segmentation, yeah, like UNet that we want to talk about today, we specify pixel label, and for each pixel we will have one label. And in instance segmentation, it's very similar to semantic, but for each object we can have a specific class. And we have also another domain, panoptic segmentation, that combine the usefulness and the utilization of semantic and instance together. And many recent papers are working on panoptic segmentation because we will have some features from the semantic segmentation and instance segmentation together. And also, I just want to highlight this, that recently the state of the art of the segmentation is Mask Dino, developed by Facebook. And the Mask Dino combined these 3 things together: the object detection, the semantic segmentation, and instance segmentation. And the reason for that is we usually have very good accuracy in object detection, but maybe we don't have that much accuracy in semantic segmentation and instance segmentation. But combining these 2 together, these treat together in one algorithm can help each other, and we will have a better segmentation accuracy at the end. So why UNet and semantic segmentation is devised? If we go to the paper, the first thing I need to highlight here is that there was some challenges back to 2015, and these authors mentioned that they won that challenges about cell tracking, and they won that challenge using UNet. And the cell tracking challenge was there was some cell images, and the problem was segmenting these cells and segmenting their borders. And there are some requirements like counting number of cells, stuff like that, and segmenting the cancerous cells and normal cells. And the problem with object detection was that it was not, as I said, it doesn't have enough localization accuracy. And some people use other strategy like using cascading window on images. So we will have this image and we will have a bounding box, and we detect for that bounding box what labels we can assign it, like image classification. So we will have one image, and with bounding box, we define each box what class can be assigned to it. But the problem with that is it's not accurate. For example, for these kind of cells that we have, the complex pattern here cannot be answered, cannot be segmented just by a bounding box and cascading windows. What these people devised by UNet is that for each pixel we can have a specific class, and for doing that, let's read some of the content of paper because it's worth to see that. They said there is large consensus that successful training of deep network require many thousand annotated training samples. In this paper, we present a network and training strategy that relies on a strong use of data augmentation to use the available annotated sample more efficiently. So one of the other things they mentioned at the first is that the UNet doesn't need that much data that we usually need for training based on the previous architecture that we had for training such segmentation. And they apply different various augmentation on images. And those augmentation, like the flipping or maybe scaling, the translation, stuff like that, could help to achieve the very good performance with less data. The architecture consists of contracting paths to capture the context and symmetric expanding path that enable precise localization. And this is the whole overview of the architecture of UNet, that there are two parts in it. Let's back to this picture. It said that there are two parts where one is the contracting path. So you see that if you have image, and for example, size of the image is 572 by 572, what we are doing here, we are increasing the number of features and we are decreasing the size of the image. That's why it's called a contracting path. So we are reducing size of the image, but increasing number of features in each channels that we can have. And after we reach to a bottleneck, we can call it like, we can, for example, compare it with variational autoencoder or stuff like that. These are some sort of features extracted from the images. So from this feature, we want to come back to the first image, but this time we want to come back in the UNet. We want to come back to the map, the segmentation map that we have. And by segmentation map, it's like an image with the same size, but each pixel is just the label of that pixel. For example, if we see this picture again, this can be a map that the background is 0 and all person, for example, here can be a pixel with value number 1. So by going through this direction, we will go to contracting path, then we will have bottleneck, then we will, using some residual connection here, and also we try to upsample and return back to the map, segmentation map that we want to train the network on it. So in the next dimension, we show that such network can be trained end-to-end from very few images and outperform the prior best method. The prior best method was a sliding window convolution network, as I mentioned. So we had a whole image, and we have cascade of boxes, sliding windows on images, and for each sliding window, we will have like classification or some other like object detection algorithm. And they show that they won the previous channel and also this channel, this challenge. So let's jump to the paper, the part that they have explained what they are doing. So I've got this picture from the original paper, and also they mention the drawback of the previous method if you have like the cascading or maybe tiling, stuff like that. And at the end, let me show you some of the example. They also mentioned that for the loss of the UNet, they use the combination of entropy loss, and also they use softmax over final feature map, and they use this combination for training the network. So we will have, at the end of the network, we will have segmentation map, and for each pixel, as I said, we have a class label. So we can apply the softmax over the final feature map, and also we can apply the cross entropy loss function. So that's the whole thing in the network. One other thing that they highlighted here is the boundary of the cells. They focus on that, and they devise some sort of a morphological operation if you want to just extract the boundary of the cells. We don't want to talk about that in depth, but let's back to the implementation. So for having this architecture, what we want to do is for each of these section, we can call them a block, and we implement each block. For example, in this picture, maybe a block includes two different steps, one convolution and another convolution. And you see the convolution is just 3x3 kernel, and the activation is rectified linear unit. And we can continue on this until we reach to the bottleneck. Then for the upsampling, we can do the up convolution, and each time we can concatenate. If you see this picture, for example, we get the feature from bottleneck concatenated from the previous layer, and we do convolution again and concatenate again from the previous encoder. So I call this path as encoder, this contracting path, and this expanding path, I call it decoder. And this encoder decoder is repeated in many different algorithms that we try to encode the image to some sort of features. And from those features, we try to decode that feature using some other information, maybe from the image directly, or concatenated to it, some sort of residual connection. And we try to decode it and return it back to something useful for us. So I just want to walk through the code that we have prepared. So as I said, we can call that each of these as block. So let's implement the block first. So for block, we will have number of input channel and how many features or output channels we will have, and we just want to assign a name to it. And for creating a block, we only have a convolutional neural network in Torch, and we will have number of input channel, number of output channel, and as we showed in the picture, we had kernel size 3, and we only had padding 1, and we don't need any bias. Then we can or we cannot have batch normalization. One of the things they mentioned in the paper, they used number of batches equal to 1, but they increased their resolution. In that time, in 2015, the advances that currently we have in GPU and the memory utilization was not that was not like today. So they used number batch equal to 1, and they don't mention a batch normalization, therefore. But currently, because we can train the model with higher number of images in one batch, you can use batch normalization in each layer. So after that, we will have rectified linear unit, and we have another convolution layer. This time, the input channel is number of features because it passed through the first convolution, and the output channel again is the feature. So by having this and passing that to the normalization, second normalization, and ReLU, we have created a block. And I remember that we covered this sequential in previous session, but if you need to again go through that and I talk about it, just leave a comment. I can walk through it. Yeah. Thank you, Sebastian. He mentioned that if we use batch normalization, we don't need bias because the bias would affect the normalization anyway. So we don't use bias, and the normalization will map the output of the convolution to the range that we need. So so far we have block, and after that, for creating that, creating that path, as I said, we have encoder path, which is this one, and we have decoder path. And for encoder path, we say based on number of input channel, maybe images is RGB or even images are grayscale. We can define it based on the UNet module that we have created. And we have number of input channels and number of features. A number of features can be defined any number that we want. But we should be careful about what numbers we select. For example, if we select number 64, we can follow this path. If we use something smaller, so these numbers from the figure should be changed accordingly. So I'll just select 32, and for having a lighter network, and we will have the first encoder. And after doing that, we are here. Now, what we are going to do is we are doing max pooling. They mentioned here we need to do max pooling, and this is some sort of downsampling of the images. We need to downsample them and increase the number of channels, decrease the spatial dimension. And by doing max pooling, we are going to the next encoder, and we continuing doing that until we reach to the bottleneck. So if you see here, we will have 4 encoder, and by final max pooling layer there, we reach to the bottleneck, which is this one, the feature image that we have extracted so far. And so we have features, and now it's time to go the decoder path and return to the mask of the images that we have. For going to the decoder path, what we need to do, one of the way is in the paper also explained about it, that because number of decoder paths is also even number, we can use transpose convolution. And one of the advantage of convolution transpose here is that the model doesn't, the model would be trained regardless of the symmetric of the input image. So convolution is somehow robust to the geometric and the some sort of augmentation that we do, positional but what I say is that we will give a robustness against positional changes on images. And when we do convolutional transpose, we're also adding this robustness to the segmentation. But if we don't do that, that would also be okay. So you will see some sort of UNet implementation in some GitHub repository that they do not implement transpose in the decoder phase. We also can use the transpose in encoder phase, but there are different way of defining these convolution and blocks. But for encoding, what we are doing now is we apply the feature to the convolution transpose, and we go vice versa. In this path, in the encoder, we are trying to increase the number of image dimension, image channel, and decrease image dimension. And in the decoder path, we are doing vice versa. So when we have feature multiplied by 16, now we want to go back one step. And for each step, when we go back, we apply the UNet block also. And each time that we are doing that in the decoder path, we also need to concat two different features from the encoder layer and encoder layer of the previous path and the features that currently we have. So let's see what we have here. Okay, just for defining that and for forwarding, that's here. So when we have the bottleneck, so now we have the up convolution, and up convolution is defined as just the convolution transpose. And then we have the decoder, but these decoder layer need to be concatenated with the encoder layer of the encoder path, and then pass through the decoder number 4, which is that block that we have created. So if we come here, instead of max pooling here, we will have up convolution, that is the convolutional transpose. So each time we do a transpose, and at the end, the image would be in the same position, return back to the original dimension. And what we are doing here is exactly the same. So we apply the up convolution, then concatenated the encoder from the encoder path, the decoder from that path, and we apply to the decoder. Decoder is the same block that we have created for encoding. And the reason that we use this information and attach them and concat them to the features that we have and then apply the convolution is very similar to the reason that why we have the residual network, because when we go through the encoder path, we may lose some of the image information in a specific layer. And the reason that the block diagram of UNet is created like that, that you see step by step in each row, just to show you that, for example, in this step, in this block, we need some information when we are doing encoding, that maybe those information will be lost when we go to the next encoding, because we are doing max pooling, some of the information will be lost. So these residual connections will help to maintain those features. When we want to return back to the segmentation map, that would be easier for the model to figure that out. So that's the whole structure of the model. And as final thing, we return the sigmoid of the output, because we want to have like between 0 and 1 as the mask of the images, and then we can return it back, that map, to any class label that we want. So that's it for the model. And what I have here is we are using the MedPy just for finding the largest component of an image, because one of the issue with the semantic segmentation is that each pixel has a specific class to it, and we may have some noises. For example, if we consider this cell, maybe one of the pixel inside that cell is saying it's related to another classes, which is not correct. And there are some post-processing that need to be applied to this kind of semantic segmentation sometimes, that to fix those kind of pixel, these post-processing usually applied by some sort of contouring, calculating the area of the contour, and if the area of contour is less than a specific, we ignore that, or we merge that with the larger connected segment. So the MedPy here is just finding the largest connected component by ignoring some of the other noises, or better say false positive or false negative that we have. So one of the other things that we need to know about segmentation is the score and metrics that we need to define in segmentation. So we know that in image classification, we may have some metrics like accuracy, F1 score, MCC, stuff like that. But in segmentation, how we want to be sure that the segmentation is accurate. So there are some metrics. I just want to show you some of them because we need them. Let me bring some images. So one of the metrics that we are interested in is IOU. And the IOU is important for us because it gives us the area of the overlap. So suppose one of these is the ground truth as one, and one of these is the predicted. And the IOU give us the how much overlap we have over the union of the prediction. And another IOU is also called the Jacquard index. So if you see these kind of terminologies, same, Jacquard is same as the IOU. We have also the DICE score, and the DICE score, let me bring that DICE score. And the DICE score is very similar to IOU, but for DICE score, let me have a better image. Yeah, for the DICE score, what we are doing here is we find the intersection multiplied by 2, and we add all of the area of the 2 segments. And there is some relation between DICE score, as you now see better, and IOU, that if you search for them as the difference between IOU and the DICE, there are some formulation that you can convert them. DICE score is also equivalent to F1 score. So if you are interested to some sort of accuracy, you can have DICE score, sorry, IOU, and if you are interested in some sort of F1 score, you can see into DICE score. And IOU is same as a Jacquard index. So there are other metrics, like for example, in instance segmentation, we have some COCO metrics that based on the IOU threshold that we define, we can have the average precision and average recall. I don't want to go through that for now, but we need to define DICE score here, and DSC here is doing the same. So as I said, we need to define based on the prediction and the ground truths that we have, how much intersection they have multiplied by 2 and divided by the whole area of the target and prediction. Yeah, and also the implementation of the IOU, the DICE score, there are some libraries that you can use them, or you can implement them based on your application. And thank you, Eugene, for putting that paper about the guideline for evaluation metric in medical image segmentation. So the first thing that we define here is just the metrics that we want to use that in training the network, or just checking and validating the performance. And the data set that we use is 3D. Let me show you the data set where we got that data from. So the data set is from brain MRI segmentation in Kaggle. So you will be able to download that. And this data set contains brain MRI images with Flair anormality segmentation mask. And the image obtained in Cancer Imaging Archive and 110 patient included in Cancer Genome Atlas and lower grade glioma collection with at least fluid attention inversion recovery sequence and genomic cluster data available. So we don't need to that genomic data cluster, but we work on the Flair data here that registered by MRI devices. And the data set structure is that we have different folder. For each folder, I think it's related to one patient because we have 110 patients. And we will have image in a slice because in MRI we have different slices. And when we load the data, we will load the volume. And one of the things here that we see in the code is when we see one mask and one input, the input is called volume because it's not only one images, it is three-dimensional images. And what we are training here is not on the 3D dimension. We are not segmenting 3D, but we are getting each slide of the image, apply it to the network, apply it to the UNet. And for each slide in the volume, we will have a mask. But we can, after this analysis, we can concat them and create another volume. That's why we keep the data structure as volume. And these kind of code just helper. If we need to them, we'll come back to them. I just want to go to the main step, run that, and if we need to this part of the code, we can return to this part. So let me run from scratch, and let me go to the GPU mode. Okay, I am. Cool. So I just initialized the model. And while it's running, let me go to the next part. Oh, it's run. And this is just helper function for cropping sample. And we have another helper function for padding to one sample. And we have another helper function for resizing one sample. Because when we want to resize, we have to go through each layer. So we have some helper function for resizing, and for normalization, and for logging, and for converting gray to RGB, and for showing the segmentation mask on the images. So I will definitely go back to this implementation, but what we need more now is the implementation of training loop for training the UNet and feeding the data to the UNet. So as we see in the paper, we have lots of augmentation. They mentioned that augmentation helped the model to be able to train with few images. So we need some sort of augmentation, and the augmentation that we use is using a sky image. We are using the scaling and rotation, and we have created two classes, the scale and rotation that get the scale value and the angle value. And these classes in PyTorch, we can define a class object, and we can apply init and call, very similar to init and forward in NN module. But this object is the Python object. But we can use these kind of object class inside the transform list, and we can use this transform list for creating image augmentation. So let me show you how we can do that. So for scale, we are creating a call function, override it, and this sample get images and masks. So when we are doing scaling, or when we are doing augmentation, this is important that we do that augmentation on both image and mask. If we just apply that augmentation on images, the model cannot learn that how it should be map this image to that segmentation map. So any augmentation should be applied on both image and target. So what we are doing here is just using the rescale function of the SK transform library, and we get image and mask, and for image we rescale them using the scale that we define, and for mask also we do the same. And there are some edge cases that if the scale is less than 1, we want to apply a padding on that, because when we scale that, we don't want to resize the image, and we have different size of the image in the input of the network. When we say we want to have like 256 as input size, it should be same for all of them. So if we are scaling less than 1, so we need to have padding beside the images. Other than that, we just do okay, and we don't need to add any other padding to the system. So this is for scaling. For rotating also, we are getting an angle, and we are selecting any random variable between minus that angle and that angle, and we rotate the image and mask altogether in a specific angle based on the random uniform distribution selected. So these two objects, when it's created, so we can pass it through the compose list. So we have a scale appended to this list, and also the rotate appended to this list, and we pass these lists, a scale and the rotate, to the compose, and compose coming from Torch Vision. And now when we want to use transform, when we want to use augmentation, we can use these two augmentation. I will show you in the next. So yeah, another thing that we use is the horizontal flipping. Same, very similar implementation as before, that we get a probability of flipping, and we pick a random number, and in some circumstances we do the flipping and return those image and mask. So just keep this in mind when we do have the training loop. When we are creating the data set, we are using this type of augmentation. So now it's time to create a data set. For data set, we call it brain segmentation data set. And as we know, the number of input channel is 3, and number of output channels, which is the mask, it's 1. And we can have the different subset like training, validation, maybe test set. We can define any other things. And you remember that in data set, we need to define init function, and also we need to define the get item function and length function. So what we are doing here is just, if we get the pass image directory, we walk through each images, we load them, we load the mask and images. And as I showed you here, so this is one of the folders that we have. So we walk through each of these, and for each of these files, we load them. Each of them is related to one slice, and we load each images and each mask slices. We append them. You see that we have imread, and we append them to the mask slice, and we append them to the image slice, and that's it. And based on if we have like a subset of validation, we just do the random sampling and separate the data set. So yeah, one of the other things, as I mentioned, that we can do is, let me bring it here, is implementing the length of the data set. So in the PyTorch, if we say length of that brain image segmentation length, it will run this override function. And for getting item, for getting one of the images, we need to get the image and the mask together. So for doing that, we have the patient slice, and for that patient slice, we also have the augmentation that we have selected. Just one thing, let me focus a little more that what happened here. Oh yeah, the transformer is here. So the augmentation is applied here that we can pass a variable transform when we initialize these classes, and we say for training data, we want to do transform. And if we say the transform should be happen, it will be applied to the image and mask. And as we define the augmentation in above, we are creating that transform list. And the PyTorch, because we use the compose, it will automatically apply the images to each element of the list and return the image and mask. So this is the whole data loader. And the final thing is just aligning, because in Torch, we have number of channel at first. In OpenCV or in NumPy, we have number of channel at last. So we will just fix dimension, and we have the torch or tensor as the output. So yeah, let me show you some of the images that I have. For image, I download them and I put them in my Google Drive. You can do the same. So I have them in my Drive in data segmentation. You need to download those data and put them in your Google Drive. And there is a link here that you can mount it in your Google Drive, so you can access from Jupyter to your Google Drive. And currently I mounted to my drive, and I can access the data using this path. So just for showing you that how these data look like. So I just use the globe library to get all of the mask and get all of the images. And then I create a training file, and using the matplotlib, I'm just showing the images with an alpha overlay of mask on it. So you can see that we have brain images and mask defined here. And for different images, we have different shape of the mask. So one of the things you need to remember here is to, if you have object detection, you cannot assign a specific location to the mask, because the object is just a rectangle. But for instance segmentation and also for semantic segmentation, we can have any complex pattern segmentation, because each pixel is for semantic is assigned to one of the label. So what we are going to do is we pass these images to the network, and we have this mask, only this mask as the target. So for training, remember from previous courses, if you're not, please ask, we have the data loader. So we have data set first created. And as I said, we need to pass image directory. We want to create train set. And also we pass image size that we want, because we have some resizing. And then we say also apply these transformation. We want to scale using this scaling factor, and we want to rotate, and also the flipping probability is 0.5. So these segmentation, these augmentation will help the algorithm to train with fewer data. And also we will have a validation set. And now we have our 2 data set. Now it's time to create data loaders. So when we say we have these 2 data set, we need to define data loader, and we talked about it. So we need to pass the data set number of batch size that we have, and batch size we have selected as 2. We can increase it based on the resources that we have. And for training, we shuffle it, and number of workers is 1. And for worker need just to having a similar data each time that we go through the generator, we can apply a worker initial ID. Yeah, and that's it. We have the training dataset data loader and validation dataset data loader. And we defined the DICE score above, but for Torch, if you want to use that in the training loop, if you want to use that in the backpropagation, we need to calculate it in tensors. So what we are doing here, we creating NN module, and this is, as I said, is calculating a F1 score in segmentation. And we will have the intersection multiplied by 2 divided by the whole area of the target and predicted. And we can also have a smooth value to the system just to be a smoothing effect on the calculating the loss. So the same thing can be applied on volume. We just apply that for calculating a volume loss, because what is important for us for one volume is for one image as volume is that all of the slices in the image is segmented correctly. So we can have a dice score as like average of that volume. What is the average F1 score, or how much the model could perform well on the whole volume of data. So next, we just get the data loader, and I think we had this one to define the devices. If CODA is available, we go through the GPU, otherwise we go to the CPU, and we have some flag here for just visualization. So every 10 different epoch, we will have a visualization, and we only visualize 2 images. So let me run from previous cell just to be sure that everything is ready so far, and that if you want to train it, because training takes a little time, and in that time you want to walk through some of the code that we haven't talked about. Of course, I try to reduce size of the images and try to decrease the training time, but so far we are just loading the data. So you see that, for example, 23 images read. So this is just one for one patient, I guess. They need to go through some of the data. We can stop at any time that without that's enough. And this is one of the way to doing that, because we have data loader and data set. One of the things that we can do is we don't need to load all of the data and put them in the memory. We can assign the path here, and every time that we get item, we can go through the path. I just use that use this implementation because to show you what other way we can do, and we should do that, especially when we have large images, especially in computer vision. So we usually do not load the images inside the memory. We just load the path of the images inside memory, and then when we go to the get item, we just get that path, load that image. That would be much efficient. In some cases, even you don't have enough memory to load all of the images. But for this case, we just use this to show you use cases. Then we will have the UNet. And as I said, we need to define number of input channel, number of output channel that we have. And yeah, that's it. And in brain image dataset, we have defined those variables. And we put that model in the GPU because we want to use that. And we instantiate the dice loss. And we use the Adam optimization and learning rate 0.001. And we go to the main loop for training the model. So if we are in the phase of the train, we put the model on train. That will help us to activate the memory on the graph that we want to backward through it. And when we are on evaluation mode, we don't need to do that. We don't need to keep the weights. And also, if we have batch normalization that we do in eval mode, we just use the variable. Or if we have some dropout, we do not use it when we use UNet eval. And we go through the data loader, and for each data we get images and mask and pass them through the GPU, and we prepare the optimizer, and with this flag that the gradient is enabled for phase train, we pass the image to the UNet and we get the prediction, and we apply this prediction and the ground truth to the dice loss, and we get a loss. Now we have loss, and if we are, and just ignore this validation phase for now, and because we are now in the training loop, now we can go and apply that loss backward and optimize one step. And that would be the whole training. But one of the other things that we are doing here is in the validation phase, we are getting the validation prediction, and each time after some frequency, we just showing some of the images and logging some of the images and their state and loss state. And that's the whole purpose of the whole pipeline of the training. And after doing the some of the iteration for going one epoch, now we in the validation set, we apply the average, we calculate the average of dice score per volume to see how much the algorithm is performing good on the whole volume. So again, I highlight this, that we apply the model on we train the model on slices, but we can evaluate it on volume. So there are different algorithms. There are some algorithms that just apply the segmentation on the whole 3D object, because there are some sort of convolution that can be applied on the third dimension. I mean, we can rotate the image and suppose that the image is seen from a different dimension. So for this case, we are only applying it in 2 dimensions. So let me, if it is not run yet, so it is still loading some of the data. Of course, I think I haven't downloaded all of the data, so it should be finished soon. So that would be the whole training pipeline. And I have logged some of the output results you can see while it's loading. So we have the training loss for each of the slices that we have. And let me go right a little bit. So for each slice in one image, you will have loss. And also during the time, you see that loss is getting smaller. Of course, there are some instability, but at least we see that losses decrease a lot. And after some steps, we are getting the average of dice score, or better say F1 score. So if starting from, for example, this is the first iteration, let's go to the next one, like 48. Yeah, as I said, this score is getting better and better, like 55. And let's go. I even didn't put it in the whole training, but in my free time, I put it in some steps to just show you. So it's increasing. And if we put that in training, like for an hour, we will see a significant result. And as just for showing you some of the output of the model, you can stop at any time, and you can go to the next part just for showing the validation, the result on validation. So for getting the result on validation, as I said, there are some way to improve the performance just by using some post-processing, like getting the largest component connected and improving the performance on the output. But for now, what we want to do is just we want to plot dice score, and also save some of the prediction images in the folder and go and see them and how they are working. I think I should be wait for running all of them. Okay, it seems that the loading is finished, so it's good that we can, in some few minutes, we will be able to run the whole pipeline and then save some of the images and show you that how it is. So during this time, if you have any question, I'm happy to answer. Okay. So while this is running, I just want to show you that what we can do in order to make this improvement. Instead of saving everything in the memory, you can do many of these steps in get item and put the weight on the hard drive, not the memory. What was the error that you got in the cell after the loading cell? If you mean the training, you mean the final Dataset score that we got? I think I have it somewhere here. Like we could get, it is just like 17 epochs. It's not finished yet, but we could get 58 from, I think, 43 to 58% Dataset score. This is what we could get just by using 17 epoch and not by using all of the data. And also, if it's loaded, good. And also, I will show you the output of the segmentation, so we can see what is the like problem that we can work on, and what is the advantage of using this method. Okay, so I was saying that we can improve this. So what we can do is, instead of walking through each image this time, we can just have all of the image paths. So we have image directory, and instead of having this for loop that takes lots of time, we can maybe copy and paste all of these into the get item function, and even the next ones to the get item function. And we don't need that for loop because we are just getting the index. So we just need to sort them somehow that be consistent when we initialize the class. And every time, instead of having this for loop, we just go to the exactly one of the index that we are referring to. So in that case, we are not loading the data. Loader doesn't take time. And each time we are in the main pipeline of training, each time we are getting one data, we just apply that, get the index, go to the directory, load the data on mask, apply these functions for resizing and stuff like that, and augmentation, and preparing data, and then return it. So that's, I think, the better implementation than this one that currently we have. Okay, good. And we have UNet now. We can start running it. So I can stop at any time. I feel that that would be enough. I can stop it. So, okay, so it start training, and after some epoch, we will see the Dataset score. So the important things I've seen in training the UNet is that usually when we resize the image, we should check that how much information we are losing. For example, if we have images with high resolution 2048 and 2048, and we convert it to 256, and we apply the segmentation, maybe we are losing some of the information in the process of resizing. We should be careful. And for doing that, maybe one of the ways is just checking the SSIM or some other image quality index after resizing and return it back to the original size. So we have one image, we resize it, then return it back and see how much information we lost comparing to the original image. If the information lost is not that much that we can ignore it, so that resize is good, because if we train a model on a lower resolution, it gives us a better opportunity in terms of the performance speed and also the performance accuracy, because in the future, if we have a higher resolution, we are sure the model will not the accuracy will not be lower than the one that we trained on. And this is usually in industry, especially, that people train the model on lower resolution and sometimes even with some of the lost information to give some robustness to the system. But in inference time, they try to have as high resolution as they can to enter to the system. So you see that there are some sort of training. It start loss from a higher value. Now we have average score 0.5. Okay. About how much information we lost. One of the approach that we can use is let me draw one thing. So if we have, let me go up and down. Maybe this is not good place to do that. I'm not good in drawing, but I will try. So if we have these images,
I think Zoom has a whiteboard option. Do you see it?
No. Where is that? Can you help me on that?
I see a whiteboard. Maybe it's just my app because I'm the host. I'm not sure. Opening whiteboard, you start share screen. Let's just try it. It'll probably temporarily stop sharing the screen for a second. That'd be okay?
Yeah.
Okay. New whiteboard. All participants can edit, open, and collaborate. There we go. All right, you can join now. Draw now.
Oh, great. So the good thing is that when we want to, the good pipeline is that when we have image, maybe this image in size, I don't know, 4096 in 4096, and when we want to train that model, we see that we cannot train it based on this number of GPU that we have, or maybe one of them even cannot fit in one GPU, even 16 gigabyte. So, for example, we want to do conversion to convert it to this size, smaller images. And what we usually do is we have these image resizing, then we convert it back. So if I can, so we have this way, and then we convert it back again to the previous size. So now we have two images with same size. We can compare them. So this comparison would be any comparison like SSIM, PSNR, maybe some deep learning quality index. There are some methods. So I just write it here just to be sure. Like SSIM, you can use PSNR, you can use some quality metrics. I don't remember their name, but there are some unsupervised image quality metrics. That depends on your data. Like if the data is scenery images, those unsupervised quality image index is good. But if like medical imaging, maybe you need to do some even manual checking by expert to see this size is good or not. Because when you have this size and you want to return back, it will show how much information will be lost. For example, I can say in many cases, like in endoscopy images, we even when we try to decrease, we will lose some of the bleeding features, because sometimes bleeding is just 2-3 pixels. That resizing in that size will lose those information. So sometimes just manual checking also good. And if it is good, so we can continue with this size. If it is not good, you have to increase it to find those features in your images. Then you can train your image with this size. So what if the image, you try to decrease it and you find out that you cannot decrease it less than this, and also you cannot train it using your current utilization, your GPU and memory. So there are some ways to doing that. One of the way is you can use some, it's called, if I remember the terminology, data parallelism. You can use model parallelism. I just want to bring you some concept, not going to the details. For example, the Facebook has a library called fair scale that can be used for model parallelism. Maybe you remember that UNet has two parts, the encoder and decoder. And the model parallelism, you can put the encoder in one GPU, you can put the encoder in one GPU and decoder in another GPU. And in that case, you will have more GPU memory when you want to do the training. And data parallelism is just like we have 4 or 5 GPU and we can use them at the same time and we split the data. So like distribution training. There are some other ways, like there are some expert model sparsing architectures that we can handle those kind of situation that you don't have enough resources. Yeah, if I can return back to the cell, save some of the data, show you, and I think I can share a screen now. Excuse me, Eugene, can you give me access to?
Yes,
Yeah.
I'll close the whiteboard. Yeah, if you can go again.
Okay, cool. So because I don't want to put it in the training on the whole day, I need to stop it in one point that I feel we are good. So far 57, not that bad. It's still not 17%, 17 epoch that I trained before, but maybe for now, for our visualization, is good enough. In the Kaggle, if you come here and go to the codes or discussion, maybe you will find some of the other kernel and see what other people got from their implementation. For example, there is UNet implementation, another here. This is with TensorFlow. So you can walk through different people codes, yeah, and see how they are doing and how much accuracy they got during the training. Let me check, for example, to just give an idea. So they're working on IOU and they could get very good result on IOU. So it means that maybe the Dataset score should be, yeah, it could go up to 90%. So we are in an earlier stage. So that's why maybe, yeah, I can stop it for now. Okay, so now what I want to do is just going to the next step, saving some of the images that we have. Okay, the directory content prediction doesn't exist. So we have now the UNet saved model. So in the next time, we don't need to run the model. And for saving, we need the content, the prediction. I just want to create a folder, predictions, to just save the prediction there. So it's now trying to save the output. Yeah, so we have this one. Yeah, I want to show you some of the images that we have. Let me open some of them. So so for some slices, because these are slices, maybe for first and end slices, because they are, you know, if you have a 3D volume of brain in first and last slices, maybe we don't have any information for segmentation. Therefore, it's good to go to the middle slices and see if the model could find something there. Yeah, you can see that in some of the slices we have some I don't know, tumor or stuff like that. And the red one is let me check. The red one was the ground truth, I guess. And these happen in one of the helper function that we have written in above. So I can go back here. Let me check that. Okay, when we are creating outline, you can see which color. So yeah, so on prediction, we are applying the red, and on the output, in the prediction, we are applying red, and in the ground truth, we are applying the green. So the green is the ground truth. And let's go back to here. So you see that even with that Dataset score, we are detecting that right. More training will give us a better accuracy in detecting the object more precisely. So there are some points here I want to.
Sorry, Mohammed. I think we're not seeing the images and some of the comments have said.
Oh yeah.
Okay.
Oh, sorry, I'm not sharing images.
Yeah, maybe you can. Yeah.
Okay, can you see now?
Yes.
Okay. So the green one, as I said, is the ground truth, and the red one is the predicted one. I just want to open the previous one just because you didn't see that. The first slice and last slice usually doesn't have even the ground truth because it's starting from a point of the brain, each layer going up in depth. And if we have, for example, you see there are 17 images. So usually the middle images should have some information. Yeah, for example, this one. So as I said, even with this amount of training, which is not trained completely, we can detect the object that we want. But the more training that we put, we can get better accuracy in Dataset score. And Dataset score means that how much intersection we could get, how much overlap we could get between the ground truth and prediction. So this is one point. Another point is that for some of the segmentation tasks, the post-processing like polygonization after that is important. Maybe in some of the medical imaging approaches, it's not important like this one because we just want to highlight the part that has any abnormality. But maybe for some other, those kind of polygonization is important. By polygonization, I mean when we have this kind of segmentation, you see that these are not smooth. So if you want to like put some points here and we say this is one of the we can represent this segment with just like 6 point or 7 point based on how much detail we have. So there are some post-processing applying to these kind of polygons to make them smooth. Even there are some method working on that part. For example, I just want to give you some hint about what other area research that people are doing. For example, there is a method Cascade PSP, and the Cascade PSP in the paper, they just talking about, if I can open that, they are just talking about that how we can improve a segmentation. For example, you see these images. This is very similar to what we got from UNet, for example. But if you want to make it smoother, if you want to make it better, there are some algorithms that just work on the post-processing part to make these smoother. Of course, this is not in medical imaging field, but it can be applied to any general segmentation fields. Like making the output smoother, improving the IOU, even with not training the baseline model, just by some post-processing. So just showing another example. This is 25 slices going to middle. And yeah, so this is good. As we said, the model in this case, this is one of the examples, the model couldn't even detect the object. I just want to bring these images. It's good to see that we need a better DICE score, and we need to train the model better because it's making a mistake and predicting these parts of the images as Tomo, which is not. And this is its call. And if we have instance segmentation, so we could have like a skull extraction, this brain tumor extraction, and we can even label them. But for now, we are just using the semantic segmentation, which assigning each label a class. So I just want to bring some of the other example, because maybe there are some images. I just want to bring some of the images that has some noises in between. I like to if we find some, because those are very interesting topics. Still, this is another one. One of the other way that people do in the post-processing when I see these images is applying some unsupervised image processing algorithm to make the prediction better. For example, if you do some active contour here, or maybe there are some method like flood field, stuff like that, you can fix this segmentation a little bit. But usually applying those some sort of post-processing need having end-to-end framework to test it every time, because you are creating your model, you're dividing the end-to-end pipeline to different parts, and each part there is a weakness in that you are losing the whole accuracy of the system. But if you can improve the UNet itself, that would be better approach. But I'm just saying that maybe in some cases you cannot improve the UNet from one point. So in those cases, still in the industry, people are using post-processing to improve the performance. And even in the medical imaging, the post-processing can even improve more than 5% accuracy in segmentation sometimes.
So when do you perform the post-processing? Do you like the example that you just showed, is that after the prediction is already done, or which step in the units do you add the post-processing part?
Yeah, the old school way is to after UNet is finished, we start post-processing. But there are some methods like the active contour gradient-based method, or as I said here, the cascade PSP method. It can be implemented as the output head of the UNet. So you can have UNet, and then you can have cascade PSP, and then train it end to end. You don't need to get the result of UNet, then train the different model on this part. Of course, this paper is trained differently because it's a model agnostic or toward class agnostic. So it doesn't rely on the your network and architecture, but you can easily assign this, attach this to the output of your network. And that's better approach, because as I said, if you split your network and architecture to different parts, tracking them and validating them and even modifying them, maintaining them would be really hard. And there is another question: is transfer learning possible in this scenario? Yeah. If you have a good encoder, and for example, you have a bunch of images trained by unsupervised method, maybe using BIOL that I mentioned in the previous session, and you have a good encoder that can bring you this latent feature, So you can use that encoder for training the UNet, and you can use those weight and just like change some of the outer layer for training the UNet that is used in some of the papers and application. That's it. I hope you enjoyed, and feel free to ask any question.
Do we have any questions coming up? If not, I think we can probably go a little bit more in detail with basically the first cell of the notebook in terms of the dimension of things, so that we understand exactly how things match between each operation, and match that with the architecture so we can see it clearly, if that's possible.
Yeah, sure.
Yeah.
I think I've seen in the previous workshop, you worked on what is the dimension when we use like a stride, when we use the dilation or max pooling, stuff like that. So when you are creating this architecture, you should be care of these values. For example, if you see here, when we are creating the encoder and decoder, so we start from the input channel, and we get any feature value. We can increase that feature value to getting more features. Sometimes having more features giving us better accuracy, because the model have access to more dictionary of features if you want to use. And but of course, it increased the size of the model, and you need a better GPU memory. And if you see the pattern that we see here is each time when we starting from number channel 3, for example, we are going to 32 number of channel, and on the other hand, we are decreasing the size of the network by 2 because we are applying the max pooling layer. So if we have, like you can see, 572 by 572, and each time, because we have, as we have here in the block, because we have padding 1, so we are decreasing a little size. So we are having 517, 570, next time 568, 568. Then when we do the max pooling, so we are dividing it by 2. So we should be careful about these values when you are doing your contraction and expansion. So if you see the pattern here, so we have features, and then we multiply feature by 2, multiply feature by 4 next, and by 8 next. Then we reach to the point by 16. This is number of 32 multiplied by 16 would be 512 number of hidden dimension feature, or latent feature, we can call it. So we have these numbers, latent feature. Now from this feature, we need to go back to the same dimension of the images. So we can do exactly vice versa what we have done here. So you can see the highlight the Jupyter create for us. So we have this value, and we convert it to the previous one. Then we have, because we are attaching, this is another part that we are attaching one of the input from the encoder layer and one of the input from the decoder layer. So that too is coming. We just put it like that because this is a dimension that we have, but we are attaching another one. That's why we multiply it by 2 every time. But we need to just return back exactly same that we have done so far for encoding. So we have multiplied by 4, then multiplied by 2, then return to the number of features and return to the output channel. So this is a symmetric pattern you can see there. And that symmetric is very important to be implemented, and be careful about the padding using a stride and dilation and stuff like that. And just one thing that you can always debug if you do mistake, do not afraid of that mistake, because you can run the network and it say, for example, these number of output doesn't match with this number of input, and we can fix that in a time.
Perfect. Thank you. Farhad, did you want to ask something too?
So in general, I want your advice for students who are, participant who needs to train a model, perhaps in medical imaging. They don't have that much of samples, and they want to use transfer learning. What is your advice? What's the best way to really utilize transfer learning for improving performance on domains where you don't have that many samples to train something from scratch.
Yeah, so you said that we don't have like any model for transfer learning, and we have few number of images. And so one of the things that we brought here is the augmentation that we could bring the value to the training. So we can have different way of augmentation. And other than augmentation, I'm thinking of the deeper the model can go, the more data that it can need. But sometimes if you train the encoder on some unlabeled data, for example, you have only 100 images sampled, but you have a database of 1,000 images and you don't have any label on them. So you can do a self-supervised training on the encoder side. And that would help us for training the deep features here. Another way is to, instead of having the output segmentation map, is train the whole UNet, but this time like autoencoder. But we should have some regularization to not just copy and paste from this way. I've seen some paper, they are removing some of these concatenation to let the model learn from different steps. Like we have input image here and also input image here. We don't have any label. We just want to train UNet unsupervisedly. But the problem we should avoid is that these residual connection, this concatenation, shouldn't enforce the model to ignore these paths. So that's why I've seen some implementation that they ignore these paths, train until this step, and get the, because this is same image, but with different resolution, with different size. So we can get the input image with different size, put it here, train a model, then go to the next step, train a model for this layer. And using the, there's called moving average weight standardization, you can reach to a point as a starting weight, a starting point for weight initialization. And that model usually, because it has seen lots of similar data, now you can use your mask instead of the original images here, and you train the UNet. This is one of the way I've seen. But other than augmentation and this way, and also maybe training just encoder using some unsupervised way, I don't remember for now any other method. Farhad, if you have, I would be glad to hear.
No, that's great. One thing that I want to also ask perhaps for your insight is that sometimes for the encoder, people use a pre-trained version of one of the known architectures like ResNet 18, and then try to create the decoder accordingly to match it. What do you think about those approaches, and in which application they might be better, for which they might not?
Oh yeah, based on my understanding, I'm not some master in doing UNet, but using some sort of ResNet or some conventional convolution network, which are already trained on ImageNet dataset or maybe other dataset, is a very good approach, because what is important for us is getting these latent feature and also be able to get some of the features from a different dimension. But we should be careful that when we are applying these max pooling and getting different layers, we should not lose that much information. I mean, some of the networks are specifically designed for a specific task, like for a classification task, that maybe some of the middle input feature doesn't have good feature to extract, or the better word was I don't remember the terminology, but we can use any ResNet or any pre-trained model that we want to train on. But what we should be careful about is that these models are trained on ImageNet, and if you are applying on the a specific image set, we should be sure that they can extract good feature from those image domain. Yeah, other than that, I don't see any problem on using them.
I see another question in the chat. Any guidelines to choose hyperparameters you can suggest? To choose hyperparameters. Yeah, go ahead.
By hyperparameter, I can say that there are some stable, as I mentioned before, there are some stable version of UNet. In stable, I mean when you train it, you don't see that much variation in the loss, and there are some stable weight definition like efficient net for UNet 2. So you can see that this is very similar to the efficient net implementation, the way that we are decreasing by 2, stuff like that. Just what we want to do is not decreasing that much in one time to lose that much information. And also when we are upsampling, do not upsample, like skip some of the step, because each step is important to maintain the higher resolution. If you see some of the paper like feature pyramid network, they are inspiring from the UNet architecture. These kind of architecture, symmetric architecture, give us a better high resolution mask in the system. So what I can suggest is just using the some of the other papers that use in the same domain data and use the same hyperparameter as they use. And also there are some hyperparameter search that you can, for small epochs, like 10 epochs, you can apply that and search on the hyperparameter space and find the optimal solution for your specific problem.
Thank you very much. If we don't have another question, I can ask a question about the loss function. So we know that there's many different more modern architecture of UNet coming along. Actually, I'm not aware, are the loss functions of the newer architectures the same as the vanilla version? Because the vanilla version is, I see in the papers it's the pixel-wise softmax over the final feature map combined with the cross entropy loss function. So softmax and cross entropy.
Oh yeah, I can bring you one thing which is interesting. Based on the application, you can define the loss. For example, in some years, people are focusing on focal loss based on the number of classes. For example, if you have imbalanced class, maybe using focal loss in semantic segmentation can be helpful. But and there are, if I can find that, that would be very good. There are some research and some GitHub repository. They just focusing on the different trends that people used for training a semantic segmentation with different loss. And in 2022, even in the some of the conferences, you see some of the very interesting loss that they consider the polygonization accuracy, they consider the segmentation resolution accuracy, they consider the IOU, DIC, all of them together. So there are some sort of loss that you can use, which is a combinatory loss of the others. I just want to bring that, but many people are using the loss that we defined here, and that can be used in many, but depends on the application. Like if it is imbalanced, you can, yes, that's it. So you can see that if we want to use, for example, a cross entropy based loss, we have different options. I will share this also with you. This is published in 2021, and talking about, for example, we can use focal loss, as I mentioned, or maybe we can have weight classes. Or if you want to use dice, we have different way. In their paper, they also mention a different loss, because when we have loss, we should take care of different things like region, like the polygon, like how much polygon can be simplified, And why I'm talking about polygons, because if you search for polygon semantic segmentation, you will find out that polygon annotation is very important. Let me show you some of the example. Maybe in medical imaging, Yeah, if I can bring some example. Polygon is very important, that even YOLO version 5 is focusing on that part. And defining the loss based on the thing that we want to train on is very important. I just want to, if I can bring some example of the polygonization that we can do. Yeah, maybe for this example, you can see that these are the points of these are the points that we can define on the polygon. So if we have a bad definition of the class, so that polygon is very hard to define. And this is very important in the industry when we wanna like send the result through API, send the result of the semantic segmentation. Instead of sending just an image, maybe we can just send 3-point or maybe 5-point as polygon representation. And but as you can see in this page, defining the loss depends on what you are caring about. Is the boundary you are caring, is the region exactly, is the polygonization is the one that you want, is the classes that you want is important. So yeah, I hope I could answer some of this question.
Absolutely. Thank you so much. And Farhad, go ahead.
It would be great if you could share this document with participants on the chat, perhaps.
Yeah.
Yes, I think you sent that to me privately. There we go. Now it's to everyone. Do we have other questions? So I have another one. Perhaps that other people may have encountered as well in terms of the annotation sort of class balance. That's in an annotation image, only a very small chunk would be, say, where the tumor is, a positive class. So and then many of the slides of an entire volume doesn't even have an annotation because it doesn't contain a tumor at all. Have you experienced some of the performance loss due to this inevitable class imbalance in the annotation for segmentation tasks?
Yeah, very good point. When we define the accuracy, that is important to define what is important for us. For example, if you have, I just give an example, if you have 100 images, and in one of the images you have 100 different objects, and you can detect all 100 different objects in that one image accurately. But for all other 99 other images, for example, you only have one object, and you cannot detect any of those objects. So what would be the accuracy? Should we say we have just 1% accuracy because we could detect one image? I mean, all of the objects on one image per 100, or we can say because totally we have 200 objects about, or 199 better. And from those 199, I could detect 100 objects. I have 50% accuracy. So which one do you prefer to have? That depends on the what expect from the system. So usually what people take care of is that even in business cases, they take care of for each image we should have exactly one. I mean, we should for each image we should have accuracy. If we have 0%, we should count it. So if you are calculating the image-wise accuracy, if there is no object on that image, you shouldn't count that image. And if there is nothing on that image, and the model say I cannot detect any object on that image, so it means that it could detect at 100% because nothing was there and nothing is detected. And so you should consider these scenarios. First, is number of objects detected per whole subset of data you have is important, or a number of objects in one image is detected is important for you. And also another thing, as I mentioned, is when we don't detect anything on image and there is no ground truth on that, is that correct? If that correct, you can count it as one of the true positive, or sorry, true negative, because nothing was there. So yeah. Also, I've heard, I'm not familiar, but I've heard that there are some null true positive that you can add to the accuracy definition, but I'm not aware of that, but I've heard of.
Yes, thank you. Go ahead.
Yeah, that's a very good point. One thing that I like to suggest everyone, regardless of which approach you use, it's really important to explicitly explain what you have done. For example, if you go with pixel accuracy, pixel level, let's say performance measures, and let's say dice score for one image that has no tumor, and your model went and picked up one single pixel there. In that case, for that one, the dice that you get is 0 for that example. So this is one approach. I don't want to say that's not correct. Some people use a batch approach. They calculate this performance in a batch style. So in that case, it is almost unlikely that the whole batch is without any contour. So they usually tend to get a better performance. The issue is not which of them is used. The issue is that most often people don't explain what is the approach they take for calculating performance. And because of that, sometimes you run a model, you see your performance is 10% less than the main paper. And when you change this, oh, this is just because of that issue that hasn't been really explained in the paper. So being explicit and transparent in your report when you design and train a model, it's really important, and help others to reproduce your work. That's my suggestion here.
Yes, thank you very much. Do any of the audience have any questions? If not, I'll just ask one last one. What would you do if the original quality of your images are just very low resolution, that you cannot do the contours and annotations very correctly? Like, for example, in microscopy images, that you just have cells that are overlapping on top of each other, that you can't really see one cell next to another. You can see that using naked eye, but that's very time consuming. In terms of the cell counting problem, I guess that's what UNet was trying to originally solve in the first place. What if your original quality of the image is just very low resolution?
Yeah, that's a very tough question, I can say. The thing is, I've had experience one of the similar situation, and in that case, we could use some sort of pre-processing before feeding the images to the model, like by enhancing some of the edges. What we've done is just we just improved the edges by another neural network just trained for extracting very similar canny edge detection, or maybe Laplacian edge detection, and we added to the images, and then we trained the network by the UNet. And in some cases, it can improve the accuracy. That depends on the texture and the problem definition. Another thing that we can think of is some of the network architecture, like feature pyramid network, are specifically designed for different resolution of the images. So you can see in many image segmentation recently, like mask2 former that introduced last year by Facebook, or mask.dino, which is introduced this year, is still in the review. So people are implementing some sort of feature pyramid network, even in transformer, like in the feature decoder parts. They try to somehow enforce the residual connection somehow. After doing some convolution, you're having some smoothness, and if you have low resolution, you're losing that information. But by having a specifically designed decoder, I can bring that paper here also. It would be interesting for maybe in the future research. So the the code is not published yet, but in the paper, they also mentioned that they are using a kind of decoder transformer using DTR. And let me just bring that, because this is some sort of the thing is, after going to the encoding layers that we get some features, what we want to do is enforcing the decoder phase by applying the different level of the encoder to the system. But this time we can have hybrid matching, exactly matching some part of the image that is more important for us, and apply those parts without any changes to the decoder. Like in the UNet, if you have some sort of this architecture, what we can do is, if so far up to here we can detect some mask with lower resolution, maybe we can highlight that mask inside here, and we say just apply this residual connection only on those parts and concatenate those parts. So it will be focused and concentrate on those parts of the image when it's doing the decoding part. So I can say in preprocessing part can be useful. Also, using some sort of a specialized decoder architecture can also be used. That we've seen, especially in a small segment that you mentioned, the low resolution is one of the challenges for a small segment. Also, is very similar to the low resolution thing, and the framework like mask.dino could outperform in low resolution semantic segmentation based on just that decoder architecture design. Yeah, that's it.
Thank you. Farhad, is there anything else you wanted to add? If not, this will.
That was great. Thank you so much, Dr. Moebian.
Yes.
Yeah.
Thank you
Thank
so
you so
much.
much.
Thank you. All right. So this is the last of this is the last of today, and we'll have another workshop on Wednesday on the best practices and pitfalls in deep learning practices, model generalizability, which will be given by Dr. Katie Owens. So we see you on Wednesday, and thank you so much again, Dr. Moebian, for being with us 3 times for McMedHacks 2022. We would love to have you again next year. Thank you so much for all your hard work, and I enjoyed it very much.
Thank you so much for your this conference. I hope that everyone could go through this UNet pipeline, and feel free to ask any question if you have any problem.
Thank you.
Thanks.
Great. We'll see you on Wednesday. Bye.
Bye, everyone.